Hi and welcome. This is our last lesson in our physics class. So we're going to today be learning about relativity. Now this is quite a huge subject. In fact, it could be a whole load of lessons all on its own. But we're only going to learn the most important parts now. And if you get a little bit worried, a little bit confused, don't worry, you can watch this video as many times as you need and then you can ask me questions in the classroom. And don't forget, we'll have a learning summary at the end for all the important bits, the bits you need to remember. Okay, so today we're going to learn, what does relativity mean? What is the theory of relativity? Special relativity, general relativity, and then some relativity examples. So first of all, what does relativity mean? What does the word mean? Well, before we get into the science of what it means, it's a really good idea if we could, understand what just the word means. So you've probably heard of being related to somebody. They're part of your family, you're related. But relativity is linked to being related. It means that the details about something have to be thought about and considered alongside the details about something else. If you look at these pencils, if you looked at just this pencil on its own, you wouldn't be able to say if it was a tall pencil or a short pencil because it had to be related to something else. We'll look at another example of this. So let's look at a 10-year-old. So this 10-year-old girl here, standing next to an adult, is quite short. She's short when she stands next to the adult. But when she stands next to the baby, she's tall. When she stands next to the baby, she's tall. When she stands next to the adult, she's short. She hasn't changed. Her height hasn't changed at all. She's exactly the same height she was. This is relativity. It means that the height of the 10-year-old depends on who you are comparing it to. So when she's near the adult, she is short. But when she's near the baby, she is tall. It's related to where she is. Another example of that is if you're in your nice warm bed and you're all snuggled up and it's lovely and warm, and then you get out of the bed, the house feels cold because it's not as warm as the bed. But if you went outside and then came back into that same house, the house would feel lovely and warm. It wouldn't feel cold because you're comparing the temperature outside to the temperature inside, as well as the temperature in your bed to the temperature outside. So relatively, when you get from your bed to your house, it's cold. But when you come from outside to inside, it's warm, even though the temperature in the house is exactly the same. This is relatively. You're measuring something depending on your circumstances, even though that thing you're measuring might be different at the time. So this is what the word means in everyday use. It just means that something that you're measuring changes depending on the circumstances, the things that are going on. But when we use it in science, it still means the same sort of thing, but it's much more complex and interesting. So what is the theory of relativity? Well, it was developed by Albert Einstein in the early 1900s, and there were two theories of relativity. The first is called special relativity, and the second is general relativity. And both of these theories relate to how things are measured differently depending on where you are and what you're doing when you measure them. So the things that you measure could change depending on your circumstances. So Einstein's theory showed that time and space were connected. Space doesn't mean space, outer space. It just means all the space that is around everybody everywhere and outer space. But his theory showed that that was connected to time as well, how time passed. And they worked together in ways that people had never even realised before. So the theories gave scientists new mathematical and scientific knowledge that they had never had before, and this took advances really far forward. And in science particularly, they were able to do atomic research and research nuclear energy and all sorts of other things. We'll look at some of the ways that the theory of relativity has helped in everyday life later on, but it was a really big step forward at the time. So what is this theory of relativity? Well, we're going to look firstly at, there's two kinds, remember. We're going to look at special relativity, and then we're going to look at general relativity. So, special relativity. Before there was special relativity, scientists believed that all motion, and motion is a movement, so it could be time because time moves forward, or physical movement like you as a person moving. But scientists used to think that everything was measured against a fixed point. So, for example, if one person was right up at the top of a mountain and another person was right down in a valley, and they both had watches, and they looked at their watches for an hour. When they came back together, both their watches would say an hour had passed. They believed that time was measured at a fixed point for both people. Wherever you are, whatever you were doing, time passed exactly the same. Just like we were talking about the 10-year-old compared to the man and then compared to the baby, the 10-year-old is exactly the same height. They thought time was like that. They thought that the time passed exactly the same wherever you are and whatever you did. And they called this fixed point the ether. So, for example, how quickly you could travel from one place to another, how much time passed in one place and another. They thought they were always exactly the same, time always passed exactly the same, but they were wrong. So Einstein said that this fixed point, this ether that they were using to measure things, it didn't exist. He said that all movement, all motion was relative. It depended on where you are and what you were doing, how quickly time moved. Have you ever sort of sat in a really boring lesson, not this one of course, and it seems to be going really slowly and an hour seems really long, but then after you might go and have fun outside for an hour and it goes really, really fast. The time is still the same, but it feels like it went quicker or it feels like it went slower. But he said that time actually was going quicker and slower depending on what you were doing, and he measured it with clocks. So this meant that the measurement of the movement of the motion depended on where the person who was measuring it was, and also how fast they were travelling themselves. So here's an example. If you were measuring how long it took you to bounce a ball 10 times, if you were timing it, bounce a ball up and down 10 times and you were timing it, and if you were standing on the ground timing this, but your friend was high up in a plane measuring it, you would end up with different times, even if you used the same type of clock that was very carefully put together. Don't worry about why this happens. We're going to talk about a little bit later, but I'm just trying to get you to see that time can move slightly differently depending on where you are and how you're travelling. And Einstein figured out that time moves differently depending on how fast you're going and where you are. So if this person here, you see this lady is in a super rocket and she's going to be far up out of the Earth atmosphere and she's going to be going very fast. But this lady is the same person really standing on the Earth. Their clocks are different because they're moving at different speeds. So another example of this might make a bit more sense is about the way that things are measured. So if you imagine you're on a train and the train's standing very, very still in the station, not moving, and you take a ball and you throw your ball south. If you were to measure how fast that ball travelled, it travelled 2 miles per hour south. 2 miles per hour south because you threw it. Now, we do the same thing again, but this time the train is moving south at 30 miles an hour. Again, you throw the ball, but you, the person standing on the train, the ball still only moves at 2 miles an hour. It hasn't gone any faster. You've done exactly the same thing. Just because the train is moving, the ball still only moved at 2 miles an hour for you. Now, a person outside the train, watching the train, would see the train moving at 30 miles an hour and would see the ball moving at 32 miles an hour because the ball moved 2 miles an hour to them and the train moved as well. So if you, the person throwing the ball, measured how fast the ball went, you would say it travelled at 2 miles an hour. But the person outside of the train would say the ball travelled at 32 miles per hour. Because to them it did, and to you it did as well. Neither of these people are wrong. They're just measuring it differently, and relatively it is different for them. The speed the ball travelled is different for the person on the train as off the train, but they are both true. I know that's quite difficult to understand, so have another watch this video, watch it all the way through, watch the learning summary, and then watch the video again. If you still have questions, please ask. Okay, so the ball is moving very fast, the person off the train, and you on the train is moving the same. That's relativity. The speed you're seeing the ball travel only relates to you. When you measure that ball, it's 2 miles an hour. Anyone who's not on the train, it's 32 miles an hour, and both of them are right. Now, we're going to talk a little bit about length contraction. Now, If this confuses you, don't worry, because this is not an important part. It's just something I want to include in case you're interested in learning a little bit extra. But don't worry, this is not the most important part. So another interesting thing about special relativity is length contraction. And length contraction is when objects seem smaller when they're going really, really fast. And it only occurs when things go really, really fast, when they go at really high speeds. They don't usually happen. So an example of this is if you're walking up and down a train and it's 2 kilometers long, the train feels 2 kilometers long when you walk up and down it. You're inside the train, you walk up and down, it feels 2 kilometers long. But if the train shoots past somebody and they're standing in the station, they wouldn't feel like the train was 2 kilometers long. It would feel much shorter because it's going so fast. Again, it depends on where you are and who is doing the measuring. Okay, so that was special relativity, and it was about how the travelling changes the speed that things travel. And whoever is doing the measuring might get different speeds for that. That's special relativity. So now we're going to go to general relativity. Again, watch the learning summary if you're still not sure. Okay, general relativity is about gravity. And general relativity is kind of the important one because it's the one that affects lots of things. So it says that time runs more slowly, which is called dilates in a gravitational field. And this just means that clocks get slower, the ticking of the clock will get slower, time passes more slowly when they get nearer to a pull of gravity. Now, we know that the centre of the Earth is a really strong pull of gravity. It's how things fall downwards. So that's one of the biggest pulls of gravity is the centre of the Earth. And the nearer you get to the centre of the Earth, the slower time runs. The slower clocks run, the slower time passes. So if you think of a big bed sheet that's pulled straight out, and you put a bowling ball into the sheet and a pencil on the edge of the sheet. Now you can see it in this picture, the bowling ball will pull down a bit of the sheet, wouldn't it? It won't stay flat. The bowling ball's quite heavy. It will pull down the sheet, and as it does, the pencil will roll down towards the bowling ball because the bowling ball is pulling down the pencil, pulling the bed sheet down. So here, the big bowling ball is a gravitational field. And with its mass, its weight, and its body, it's pulling the pencil towards it. Now, if you think about all of the space around us is the sheet. Really big, huge things pull down the space around us, the sheet. They pull down the space around us. And the bigger the ball, the more that the sheet it pulls down, the more space around us it pulls down. It causes a gravitational pull. So the effects of this gravitational pull are too small to record. They're not things that we can record on planet Earth, really, because they're much, much, much too small. But when you get into outer space and things like that, and big scientific experiments, they do make a difference. But it's worth understanding. So if the bowling ball was a planet or something else really, really big, the gravitational pull it had would be enough to slow down time quite considerably. So again, the sheet is the space, and the bowling ball into the sheet pulls it down, like in the picture here. It pulls it down. And anything that gets near enough to that pull will slow down. Time will slow down because it's being pulled in. This is an example of what Einstein has said. Objects bend the space around them. Just like the sheet, we bend this, even you, we bend the space around us. So if you take a normal ball and you throw it near an elephant, it will curve slightly, not a lot, because even though an elephant is really heavy and huge, it's not big enough to make much of a difference in our space and gravity. But you throw the ball and it will curve slightly towards the elephant as it passes, because the elephant has a pull, a gravitational pull, like the elephant on the sheet would pull things down. It's pulling down that ball, only a tiny bit though. This is because the elephant's size, its mass, is generating gravity and bending the space that is around it. Also, the more mass something has, like the elephant, the more this has an effect. So the elephant, the elephant will have things curve towards him more than things will curve towards you because you have less mass than an elephant. So again, think about the big things are pulling gravity towards them. They're pulling things towards them, just like the sheet. They're pulling it towards them. But when things get near to gravity, time slows down. All objects bend space around them, even little children. But it only becomes very noticeable, and you can only actually measure it with big objects like planets. So let's look at some more examples so this makes a little bit more sense. If your friend climbs the very top of a mountain and he looks at his clock, his watch, he won't know, but when he compares it later, his watch will be going faster than another friend who is at the bottom of a valley, whose watch will be going slower. Time will be passing slower for the person at the bottom of the valley than the person at the top of the mountain. And the reason for this is because the person in the deep valley is being pulled closer to the center of the earth. They're right near this gravity pull, that pull of gravity. So they are going to be slower. Just like if it was an elephant, if they were nearer the elephant, they were near a big bowling ball, they have been pulled in and their time slows down. Whereas the person far away, right up at the top of the mountain, far away from the gravity pull, his time doesn't slow down. It's faster than the person who's near the gravity. A very real experiment was carried out doing this. They took very precise clocks. Precise means very exact. And they put them on special airliners that were flying 1 millionth of the speed of light. And they flew around for 2 days continuously without stopping. And the time that was on the clocks was different to the time that was left on Earth. And this is because relativity told us that this is what would happen. This is how it is. Now, why was the time different on the plane than it was on Earth? Well, because the speed of the plane was going really fast. And special relativity has told us that the speed is different. Like the person on the train measuring the ball, it's different for them than someone off the train. So the person on Earth had a different measurement of the time to the person in the plane. That was special relativity. And because the plane was further away from planet Earth and the gravitational center of the Earth, and the clock that was sitting on Earth and not in the plane was nearer to the gravitational pull, time was slower for that clock. So that's general relativity. So all of this isn't just for scientists to think about. Relativity is very important in nuclear energy and the creation of power sources. It's very important for all sorts of things like that. Now, before I move on, I want to talk about something that's not actually on these slides. You may have heard of this, or you might not have heard of this, but there's a special equation, a special mathematical sentence called E equals mc squared. Now, I didn't really touch on this in the slides because it's not the most important thing, but it's something you might be wondering about. This is how Einstein wrote. This is how he wrote down the theory of relativity. And the reason he wrote it like this was because E is for energy, and m is for matter, and c squared is for the speed of light. So if you think about energy being the thing that is being the pull of energy, we talked about energy before, matter being the object, the heavy thing that's pulling you down. So energy is the pull of, matter is the elephant, energy is the pull the elephant has, and c squared is the speed. So energy is equal to the object and the speed. That's why it's energy equals matter by speed of light. Don't worry too much about that. I just wanted you to know what it was in case you were wondering about this equation. That's just how Einstein wrote down relativity. Energy equals mc squared. The energy that is created by the big elephant is pulling down time, slowing it down. Okay, so another example is our GPS, our gravitational positioning system. You might have seen GPS in the car. You might have been lost and needed it. I use it all the time. It's like Google Maps. We use it to get around. And how that works, our satellites above the Earth can find out people's positions by the technology that we use in our cars and things like that. But these satellites have to use relativity laws, theory laws, because if they didn't, they wouldn't know where people were. For example, the satellite is really far away from the gravitational pull. but you and your car are quite close to the Earth's gravitational pull. So what's going to happen? Your clock is going to be going slower than the satellite's clock. So that satellite would be thinking, well, it will take them 10 minutes to get that far. So in 10 minutes, they'll be there. Whereas you in the car, it will be much, much slower. It might take you 15 minutes because you are nearer the gravitational pull, your time goes slower. So satellites have to take this into account when they navigate people, and it's important that they know how to do this, or they wouldn't know where anybody was, and they wouldn't be able to navigate. It's not just for people driving in cars, it's also for rockets and things like that get sent into space. NASA and all other countries as well that have to keep a close eye on space objects need to know exactly where their rockets are, and they have to think about relativity to know that. Okay, let's do the learning summary. Again, if there's anything you're not sure about, please watch it again and then ask in the classroom. So, relativity means that when something is compared to a different thing, like the height of the 10-year-old, if we compare one thing to another thing, it will be different depending on the circumstances of the comparing. Albert Einstein discovered two theories of relativity, special relativity and general relativity. Scientists used to think that time measured the same no matter where you were or what you were doing. That's what they used to think. They used to think that time was the same for everybody. But Einstein figured out that that wasn't true. Movement and time changed depending on where you were, when you measured it, and how fast you were traveling. So the time that only measured that you measure is only true for you, not for someone else measuring it if they're in a different place or going a different speed. So general relativity is similar to special relativity. It still says that time and movement is measured differently. But general relativity looks at gravity. If something has a strong gravitational pull, not only does it pull down other things like the pencil, but it also pulls down time. So clocks will run slower if they're pulled down by gravity. And here is that picture again of the lady on the planet, and her clock is running much more slowly than the person on the plane or on the rocket. You can see that when they set off, the lady on the planet, they were both at 0. The lady on the plane, she was at 0. And she went off and flew round and round and round. But when she came back, she had only gone for 5 minutes. But this one, the lady on the Earth, she'd been gone for 25 minutes. So time is different depending on where you are and how it's being measured. Okay, I really hope all of that made sense. Again, please ask in the classroom if you've got any questions. Don't feel bad if this is a little bit confusing, because when Albert Einstein figured this out, there were only around 6 people in the world who could understand this. It's one of the most complicated scientific theories there are. But more and more people have been able to understand it and look at it and explain it. So if you can understand it, you are one of the brightest people in the world.